Welcome back to chapter 23. This is the second video in a series of 3 that we'll have for this particular chapter. In this video, we're going to look at generators and motors, and we will also look at this topic in lab because I feel like it's one of those things where you need practice. So we will attempt to practice. All right, so what is a generator? A generator, looks like I need to come down a little bit. A generator, sometimes called a dynamo, although not usually these days. A generator takes mechanical energy and turns it into electrical energy. So a generator will need some sort of magnet. It will need a wire loop. Typically, it's lots of wire loops, not just one. And it will need a source of mechanical energy. So a magnet, a wire loop, and a source of mechanical energy. And we have a little demonstration generator that I'll bring to class for us to look at. So with this, you supply in this diagram from the textbook, your hand is turning a crank, and that crank is turning this loop of wire inside this large external magnetic field. And the result will be that as the wire turns, it experiences a change in the magnetic field. And we know that if a wire experiences a change in an external magnetic field, it's going to generate a magnetic field around itself to oppose the change. And the end result will be that there'll be a current produced in the wire because of that opposing magnetic field. And if we hooked it up to a little meter, we could measure it, or if we hooked it up to a little light bulb, maybe we would power the light bulb. In the old days, it was quite common to see on bicycles little generators, and as you pedaled, you could power a headlamp. So the rules that we're going to use will, whoops, I overshot that. I'm not quite sure how that happened. Let's back it up. So our rules will be, we're going to draw in the external magnetic field lines. We're going to draw in the direction the wire turns, because those will be 2 things we'll know. Then we'll draw in magnetic field lines around the wire to oppose the motion. This is because of Lenz's law. And then we'll draw in the current based on those field lines around the wire. And then we'll label the contacts plus or minus based on the direction of the current. So our rules, magnetic field lines go from north to south. The plus goes with the X and the minus goes with the dot. This X and dot are referring to the X and dot we use with the right-hand rule. When current is coming into a page, it's an X, and out of a page, it's a dot. When positive current, that is. The wire is going to turn because you force it, and the induced current will oppose the motion. So the magnetic field lines from the magnet and around the wire will look as if the wire is going to go in the opposite direction. If we had stationary contacts, we would be creating DC current. If the contacts could actually move with the wire, we'd have AC current. All right, let's get to our diagrams. So here is our first example. And like I said, we're going to work on these in lab. So the first example, we have our north pole on the left and our south pole on the right, and we're going to turn the wire counterclockwise. So this is an end-on view, a cross-sectional view. So the N and the S, these are the ends of the magnet. The circles represent a cross-sectional view of the wire. It's like we slice down through it, and we're looking down the length of the wire, and we can see, is the current coming towards us or away from us along that wire? So first thing, draw in those external magnetic field lines. They always go from north to south. So that's what I've done. I've drawn them going from north to south. And we were told that we're going to turn this counterclockwise. That means that the wire on the right-hand side is going to move up. That's what this little arrow is about. and the wire on the left-hand side is going to come down. That would make it swing in a counterclockwise direction. We would be rotating in a counterclockwise direction if that happened. All right, so we have these arrows, the curved one on the outside from north to south, and the one on the right going up and the one on the left going down, because the motor turns, the generator turns counterclockwise. We have these arrows in because of what we're given in the problem. Now we have to think. And the thought process is that the field lines around the wire have to oppose the motion. They have to oppose the motion. So we only pick one wire and we only pick one of the two outside field lines. Everything else will follow in a pattern. So let's look at the one on the upper right-hand side. We know that the outside magnetic field goes from north to south, so it's pointing to the right. We know the wire comes up. We had to draw a field line around this wire that would make it go down, that would oppose the motion. And so you see, I drew a field line that points in the same direction as the outside one did. So the outside one points to the right. The one I drew around the wire on just the top part also goes to the right. Like magnetic field lines would repel each other, and that would push the wire down. We know the wire goes up, so by drawing a field line that would push it down, that would resist the motion, we have our field line going in the correct direction. So if it goes to the right at the top, it'll swing around and go to the left on the bottom. And the one on the opposite side goes on the opposite direction. So it'll go left on the top and to the right on the bottom and swing around. And now all we have to do is use the right-hand rule to decide which wire gets the dot and which wire gets the X. Remember, on the right-hand rule, you've got your thumb, that's the direction of positive current, and you have your fingers. So if the thumb is pointing at you, and the way I have it drawn in, the thumb pointing at you should be the one on the left-hand side. If you look at it, if your thumb is pointing at you, your fingers across the top would curl to the left, and that means this one, the wire on the left-hand side, is going to get the dot. If it gets the dot, the wire on the right-hand side gets the X. Once you pick out which one gets the dot and which one gets the X, the plus goes with the X, the minus goes with the dot, and then we're done. Generators can never be 100% efficient because of Lenz's law. There's always going to be a reduction in the current because of this resistance to the effect. And that, in fact, it's called the motor effect. So you can't ever make it win 100% of the time. So for practice with this, you've got north on the left, south on the right, turns clockwise, south on the left, north on the right, turns counterclockwise, south on the left, north on the right, turns clockwise. So we have 3 more things to practice with. Let's look at electric motors. They are a little easier. They're very similar to generators, but there's a distinct difference. So they need a magnet, just like the generators. They need a wire loop, just like the generators. But instead of a source of mechanical energy, they need a source of electrical energy. So you have your wire loop going. This is an overhead view in the north and the south poles of the outside magnetic field. And you can see it's showing that this wire loop is rotating or spinning in that outside magnetic field. So to do this, and as it turns, it creates electricity in the wire. I'm sorry, the motor has electricity in the wire, and as it the magnetic field around the wire interacts with the outside magnetic field. That's what makes the motor turn. So our rules are going to be that we want to draw in the external magnetic field lines. We want to draw in the direction of the induced magnetic field around the wires. And then we'll look at the interaction of those two magnetic fields to decide which way will the wire be forced to turn. And it turns in the direction that these two magnetic field lines make it go. All right, so the rules are magnetic field lines go from north to south. The magnetic field lines around the wire follow the right-hand rule, and plus will go with the X and minus will go with the dot. And that the magnetic field lines interact to move our wire. So the magnetic field lines are the reason the wire turns. There's no trickery. Okay, let us look. Whoops, didn't mean to do that. Let us look at our first example. So our cross-sectional view, north is on the left, south is on the right, plus is on the right, minus is on the left. So first thing, you draw in the external magnetic field line. So we go from north to south. We know that plus gets the X and we know that minus gets the dot. So the X and the dot. And then you use the right-hand rule. Remember, your thumb is the positive current. If it's coming towards you, it would be the one on the left-hand side. The dot is your thumb pointing towards you. Your fingers curl to the left across the top when that happens. So on the going away from you, it would go to the right. And now we can look at the interaction of these magnetic field lines. And you don't have to look at all of it, just pick one pair because the other side will go in the opposite direction. So if we look at this outside magnetic field line, the one on the top goes to the right. On the wire on the left, it points in the opposite direction. So outside field line is going to the right. On the wire on the left side, it's pointing to the left. They're opposite directions, opposites attract. That means that these two magnetic field lines, the outside one on the top and the top one on the left wire, attract each other. The magnetic field lines attract each other because they point in opposite directions, and that will pull this entire wire up. And if the wire on the left goes up, the one on the right comes down. When the one on the right comes down, we're moving clockwise. And that's all there is to it. So motors turn, in this case, this one's going to turn clockwise. Motors can never be 100% efficient because of something called the back EMF. So what is the back EMF? Well, the back EMF is a little tiny voltage induced to resist this current in the wire. So we know that we've got positive current coming out of the paper on the left towards us. There's a little tiny current created to reduce that and a little tiny potential to reduce this. Remember, there's always a little resistance to change in nature. So this little tiny back EMF reduces the total amount of current just a little bit. And in fact, motors are designed with that in mind. A motor is designed so you never anticipate that it will carry the full amount of current through the wires, which means that if your motor stalls, so when would that happen? Well, I've had a motor stall when I'm trying to use an electric drill, and either my drill bit is dull or my material is particularly difficult. But if the drill stops turning, then the wire stops, the coil of wire stops turning, and there won't be any back EMF, and there'll be too much current passing through the loops of wire in the motor. And the end result will, if you keep trying, if you're going to burn the insulation around the wires, because the wires get hot when they have the maximum amount of current going through them. Another time I've had a motor stall is in my kitchen. If I have an electric mixer, and sometimes the beaters cannot manage whatever it is I'm trying to mix, in particular with cookies. And so the end result will be that the motor will stall and it will overheat and problems will arise. We will stop with this and we'll do transformers in the next video.